So today we are going to do our next lecture, lecture 16, and we'll continue things that we were seeing last time about the column space. So I'll rewrite that example that we had started with. So our objective was to take this matrix 1, 2, 3, 5, 2, 4, 8, 12, and 3, 6, 7, 13. And our objective was just simply to find the column space of A, or column space of the matrix J. Okay. Now, we had seen a few things, so let us recall. We had seen that the matrix J can be reduced to a matrix U, which was in echelon form, which could be further reduced to a matrix R, which was the reduced echelon form. We figured out the following thing, that the column space of J is not the same as the column space of U, which is not the same as the column space of the matrix R. So their column spaces are not the same. However, since the pivot columns are the same, so that gives us the information of what we're looking for. Okay, so this tells us which columns I should be using in order to find the column space. So one of the descriptions we had given, so I'll call it as the first description. Of column space of J. We said this is all those vectors b1, b2, b3 such that b2 plus b3 minus 5b1 was 0. This was our first description. Which are the right hand sides which could possibly give a consistent system. Then we said we want to see if we can give alternate descriptions of it. So let's try to see alternate description of the column space. For that, we need our matrix U. If you recall, we had reduced J to the following matrix, which was 1, 2, 3, 5, 0, 0, 2, 2, 0, 0, 0, 0. And then we had also a reduced row matrix, which was 1, 2, 0, 2, 0, 0, 1, 1, 0, 0, 0, 0. Okay. Now, the pivot entries are going to be the same in all the scenarios. The pivot columns will be the same. So for example, out here, this is my pivot column, this is my pivot column. Out here, this is my pivot column, pivot column. So as you can see, the pivot columns are the first and the third in all of these matrices. And that is the information that we want to exploit to our advantage. So let's see how does this help us. What could be an alternate description? See, what I can do is I can also say that my second description of my column space would be as follows. I can say it is the linear span of the pivot columns of J. Now, why is this such a better description for me as opposed to, I wouldn't necessarily say it is a better description, but it gives you another perspective. And we could have simply said that things which are of the form alpha times 1, 2, 3 plus beta times, remember it's the first and the third column, 3, 8, 7, where alpha and beta could be any real numbers. This is another description of the column space. Both have their own significance, both have their own importance, and both provide us the information that we're looking for. For example, advantage of this description is I can give me a vector, I can test it immediately whether it is in the column space or not. Advantage of this thing is it is telling me what are the minimal set of vectors I need in order to create my column space. It says anything which is in the plane of these two vectors would be in my column space. So in some sense, it is telling me that the other two vectors in the column were redundant. I really didn't need them, but these are two basic ingredients I need in order to generate everything else. So as you can possibly see, it's a very simple observation why other vectors are redundant. If you look at the second vector, it is a multiple of the first vector. So that means whatever side vector is doing, I can get it done by the first vector itself. If you look at the last column is actually the sum of the second and the third column. So that means I can replace the last column if I have the second and third columns. The second is dependent on first. All it is telling me is the first and third column are the ones which are creating the entire show. So that way, we have the description of the column space in terms of bare minimum columns, which would help me make my column space. Okay. Now this actually brings us to the topic that we have been aiming for up until now, and that is the idea of something we call as the basis of a vector space. So let's try to discuss things about what a basis means for a vector space and how is that relevant for our details. Remember, I have not talked about the other two spaces yet, and there's a reason for it. I first want to get to know basis, and possibly that can help us with other stuff. So what exactly is a basis? So before giving you a technical description, I'll first give you sort of an intuitive idea about what a basis is, and based on that, we'll be able to capture what we are after. So think of basis as some kind of an ingredient list you need in order to build up what the object that you want. So for example, if you think of making a cake, then maybe milk, sugar, egg, flour, water, these are the basic things which you need in order to make any cake. So you take some linear combination of these ingredients and you make up the object. So that is the idea of a basis. You can't drop water out of your list, you can't drop milk out of your list, otherwise you won't have a cake. So what is the bare minimum set of vectors I need to create everything in my vector space? So I want to cut down on redundancy, and based on this, we come up with the following definition. So suppose I have a set of vectors. So base is a set of vectors. I shouldn't say it's a set of vectors. Let me correct myself. Let me redo it. Suppose I have this set of vectors which is linearly independent, and the span of the set gives me the total space. Then the sequence I'm using these special brackets so that we know that order is of importance here, is a basis of V. Now, if you recall my example about the cake, I said you cannot throw water out or milk out of the list, otherwise you won't be able to make a cake. So in some sense, that is the idea behind span. You can't throw things out, otherwise you won't be able to make anything in the vector space. Moreover, whatever water does, milk perhaps cannot do that job, or whatever milk does, sugar cannot do that job. So in some sense, they are both independent of each other, their functionality is independent, and that is why we need all our ingredients or all our vectors to be linearly independent of each other. So if you have these two features, then the set can create a basis for you. Now, notice the difference. Earlier I started with a set, and now I'm insisting on sequence. That means order is important. In our present context, you may not see the virtue of the ordered basis. However, it should be kept in mind that a basis should always be specified with the order. And later on, when you do things like coordinate system, that is where things start to matter more. So get into the habit of saying that basis is a sequence of vectors rather than just saying basis is a set of vectors. However, I should repeat that you will see me using basis as a set all the time, at least for this particular level of the course. But still, it's a good idea to keep this in mind. So let's take our vector space as R2. Suppose I am given this set of vectors 1, 0, and 0, 1. I claim that this definitely forms a basis. And the reason for that is, for obvious reasons, it is a linearly independent set, because the vectors are not multiples of each other, and everything in the span of this set, if you look at the span of this set, I claim that it is R2. Because if I pick any vector AB in R2, I can write it as A10 plus B01. So any vector in R2 is going to sit inside the span. And for sure, a span of this two-dimensional vectors will definitely be a member of R2. So the other way set inclusion is obvious. So definitely the span of B is that R2. So it is a basis. It's a linearly independent set, and it gives you everything. If I drop one of the vectors out, I can't span R2. If I throw in one more vector into this thing, it is kind of going to create dependence, and that will violate the condition on the basis. Now, let me say something about the reason I am insisting on the sequence. For example, when I give you a point in two-dimensional space, I give you the point, let us say 2, 3, and you very well jump to the conclusion that 2 is the x component and 3 is the y component. Now, the reason you say that 2 is the x component is because we have stuck to a convention that the x coordinate would be put first. And this is where the sequence in the basis comes into effect. So if I write 1, 0, and 0, 1, this is what we call as the standard ordered basis. That means it is the basis that we are sort of used to, the x coordinate first and the y coordinate second. So then that means whenever you tell me 2, 3, I'm always going to assume that 2 is the coefficient of the 1, 0 vector and 3 is the coefficient of the 0, 1 vector. However, if you decide to change the order of these vectors, there is nothing wrong with it. They are still independent. They can still span whatever you want. But then in this system, 2, 3 would mean something very different. 2, 3 would be a combination of this, which would be a very different vector from what you initially suggested. So 2, 3 would be this. So in some sense, it will be a very different point than what you had in mind. So just saying coordinate system 2, 3 doesn't end the story. It tells you which ordered basis did I use. So as a basis, these two are different bases because the order of the vectors is different. As a set which creates basis, they are coming out of the same set P. So please bear in mind that order is of importance, especially when you are trying to apply the coordinate system. If you change the order, you may be talking about a different object within the same vector space. Okay. Now, remember every time I have used a word, a basis. I never said the basis. That means there could be more than one basis for a given vector space. So you may say, oh well, it is obvious. If you change the order, you're going to get a different basis. But is that the only reason? Or can I create a completely different basis, not made up of those vectors? For example, instead of using 1, 0, 0, 1, could I have created another basis, maybe of different vectors? So for example, could I have another basis, let me call it as B2, which has the vector 1, 0, and pi e. Could this be a basis? If you think a little bit, these are linearly independent. So B2 is a linearly independent set. And it may not be that difficult to prove that I leave to you that the span of B2 is actually R2. It may be not as obvious as this in here, but I still feel that we can prove it, that the span of B2 is R2. Why don't I give it a shot and try to prove that span of B2 is actually R2, so that we are convinced that this is indeed a vector basis of the same vector space. In fact, let me try a slightly different approach, which may bring up a very general point for us. Remember, we said here is one possible basis. Okay, I'm not really going for the order right now. And we said, I'm claiming that could be a possible basis. Think of basis vectors as generators, which are generating the entire space. So if I can generate the generators, then that means I should be able to generate the entire vector space. So what we will do is, we will try to show, this is our aim. We will show that the vectors in B2 can generate the basis vectors from B1. So this will show that the span of B1 is going to be sitting inside the span of B2. And that will take care of what we are trying to prove. In fact, the other way span is obvious because we already know that vectors in B1 can span everything. So they can definitely span those two guys in B2. Okay, so how do we show this? Well, let's see. Let me give these guys some names. Let me call this as V1 and V2. Let me call this guy as W1 and W2. Question we are asking is, can the vectors in B1 be written in terms of vectors in B2? So for example, V1, I can write it as 1 times W1 plus 0 times W2. So can I say this means V1 definitely falls in the span of V2. In fact, V1 and W1 are the same vectors. So let us say this is V1 and this is V2. What about V2? Can V2 be written as a linear combination of the vectors W1 and W2? See, if I can show this, then would you agree? It will tell me that the vector V2 also lies in the span. So if V1, V2 lie in the span, so their span lies in the span of V2 because the span of V2 is a subspace. So this is the only thing which is in front of me that I need to show you. How can I produce 0, 1 using vectors from this? Okay. As you can see, it boils down to solving the system of equations, and by now we should have an idea how to do this. So the question is this a consistent system or not? That's it. All I have to do is convince you that it is a consistent system. Now, you're sure it is a consistent system because the rank of this matrix is 2. As simple as that. I don't really need to find you the answer in particular. I can simply claim that the rank is 2, hence the system is consistent. You have 2 pivots, so any right-hand side would have done the job. But the reason I wanted to have this idea behind the proof is because we're going to use this idea very soon. That trying to write the generators in terms of the other set of generators. So this tells us that there could be more than one basis. In fact, any vector space on on a nice field. When I say nice field, I mean things like reals or complex. Any vector space will have infinitely many bases, not just because of the rearranging of the order, but you could have completely different vectors inside a vector space and will form a basis. So now the question is, if I have infinitely many bases, for example, I gave you examples of two bases, B1 and B2. They don't have anything in common except maybe the first vector. But since I said I could have a completely different basis, what is the guarantee that all the bases that I will have the same number of elements? If that is the case, then at least one thing is sure, that my basis could be anything I want, but at least the number of vectors in each of those bases would be the same. And that is what we will call as the dimension of a vector space. So the concept of dimension hinges on the fact that all bases have the same number of vectors. So if you remember our examples from the null space that we just discussed, if you remember the second description, the two independent vectors which are spanning the space were forming the basis. So now we want to find out the idea of a dimension. Our focus will be on the so-called finite dimensional vector spaces, just so that you know there are infinite dimensional vector spaces also, and their definition of basis is a little tricky. So what is the idea of a dimension? This is how we are going to define dimension, and then we'll show that this definition makes sense. Dimension is basically the number of vectors in a basis of V. So in some sense, we are sort of assuming that this definition makes sense only if all the bases have the same number of vectors. We don't know that thing yet, but we'll prove it and hence validate this particular definition. So suppose we have a vector space V, and suppose I have a set B1 and a set B2. So let us say I have a set B1 with n vectors and set B2 with m vectors. Such that both B1 and B2 form a basis of V. Then n must be equal to m. Okay. We will use this, the idea that I showed you over there, in order to prove this. I'll give you a sketch of the proof without getting into the details but that sketch will be sufficient enough for us to understand the general idea behind the proof. I would like you to complete the details. In fact, I'll give you more than a sketch. I'll give you pretty much the skeleton of the proof with only few details left out. As you will see, writing the skeleton would take more time than anything else. So how does the proof go of something like this? Remember, my idea in that example was to write each basis vector in terms of the other basis vectors. So for example, if I'm claiming that both of them are basis vectors, that means I will be able to write W1 as a combination of the vectors in B1. So since B1 is a basis, this implies that I can write any vector W, for example W1, as a linear combination of vectors in So I should be able to write W1 as this, then I should be able to write W2 also as this, and so on and so forth. Now, let us assume that M is bigger than N. Okay? So in some sense, if I do this, then can I say let me try it and see if I can make it work. So here's my vector V1. So I'm creating a matrix of my vectors V1, V2, Vn, and here is my matrix A11, A21, An1, so on and so forth. And here is my W1, W2, so on and so forth. So each W1, for example, W1 can be written as a linear combination of VIs, W2 can be written as a linear combination of VIs. So this is what we are capturing. So this is my matrix W, this is my matrix V, that is my matrix A, and so on and so forth. Okay, I'll just make one change because I have written the matrix in a slightly different way than I previously intended. So I will say let N be bigger than M. Without the loss of generality, I can do this. It's just that if I had written the other way, I would have made M bigger than M. Anyways, if you look at this setup, it looks very nice and all that. What is the size of the matrix A? A is a, let's see, how many rows and how many columns? A is a n rows and m column matrix. Actually, let me see if I need to change that assumption. Let me change my mind. Again, let me call this as m bigger than n. Just that one mistake on my part. It's kind of spiraling this. Okay, so A is an n by m matrix. If A is an n by m matrix, you have, so can I say that the rank of A can be no more than n, and in particular it will be less than n. This means there are non-pivot columns in A. This means there will exist a non-zero vector such that this guy has a non-trivial solution. Because of the presence of non-pivot columns, or you can say columns which are dependent on the pivot columns, there will exist a non-zero solution to that homogeneous system. What does this tell you? Well, this actually, instead of giving you the sketch, I'm giving you the entire proof now. So what does this tell me? This tells me the following thing. So now if I look at that solution that I've got, what would be Wx? It would be simply V times A times X, but this is 0. So this implies the homogeneous system Wx is equal to 0 also has a non-trivial solution. Now what does this tell you about the columns of W? This means the columns of W are not independent. But remember, the columns of W came from the basis B2. This implies B2 cannot be a basis. So we have reached a contradiction. So that means our assumption that m is bigger than n is wrong. Similarly, you can show that n cannot be bigger than n for the same reasons. Hence, the only choice we have is that m must be equal to n. So given any two bases of a vector space, they should have the same number of basis same number of vectors in the basis. Hence, the definition of a dimension makes sense. Now we can simply say dimension of R2 is 2, because I just need, any basis will have two vectors. Dimension of R3 is 3, because any basis of R3 will have 3 vectors, so on and so forth. So this is the concept of dimension that now we have taken into consideration. Using this dimension business is a lot easier on us, because it will help us understand more things about vector space. And every time we can use the word dimension without any ambiguity now. So you'll see it's a liberating experience. So let's introduce some names. So dimension of the column space of A, as you can see, is the number of pivot columns and this is the same as the rank of A. Dimension of the null space of A will be the number of non-pivot columns and we will call this as the nullity of A. And as you can see, our description gives you this for free now. Rank plus nullity of A is actually the total number of columns of A. Remember, the non-pivot columns are the ones which are responsible for giving you the null space. If everything was a pivot column, then the only solution is a zero solution. Now, what is the total number of columns of A? If you think A to be a linear transformation, then the total number of columns of A is actually n. If A is a m by n matrix, which is same as the dimension of the domain space A. So we have proved what we call as the rank nullity theorem. There are better ways of proving it than what I showed you, the way I showed you. But right now, I wanted to confine ourselves to things which are easy to understand at this level rather than giving a very sophisticated proof. And this is something which helps us understand quite a few things about rank and nullity. So for example, one might ask a simple question like this. Find a matrix A whose column space has a basis 1, 2, 5, 6. And its null space is all the vectors A, B such that A is equal to B. Something like this. It's a very long descriptive question, but you'll see the answer is fairly straightforward. Find a matrix A whose column spaces has a basis this, its null space is this. Look at what I've given you. The dimension of the column space, the dimension of the column space of A according to this must be 2. What about the nullity of this? Nullity of this is 1 because it's being spanned by one vector, namely 1, 1. So whatever you are dealing with, your domain space, so your domain space must be 3-dimensional. So whatever matrix you are thinking about, it has to have 3 columns. So you need 1, 2, you need 5, 6, and you need something over here. Okay? So question is, can you put something in over there so that you get what you want? Then the null space is equal to that, and the column space is equal to that. Well, question is what can we put as stars, or can we even choose anything in terms of stars? What do you say? Let's see, we can do this, or are we setting up against something impossible? Okay. If the dimension of the domain space must be 3, then would you agree that the null space would be a part of the 3-dimensional vector space? So definitely the null space cannot be a subspace of 2-dimensional vector space. So that is kind of ridiculous for us to even ask this question. Such a thing cannot happen because the null space will not be fitting inside this. So we want null space to be a subset of R2, whereas in our situation, A has to be a 2x3 matrix. According to this, the null space must be sitting inside R3 and not R2. So this is definitely not possible. So you can't give me a matrix whose column space has a basis that and null space has a basis this. Question is, what if I give you a different question? What if I had given you something slightly different? So again, find the matrix A such that column space has basis as before, 1, 2, 5, 6. But this time I changed my null space requirement, and null space has basis as, say, 1, 1, 1. Is it possible? Again, rank plus nullity is 3. So A must be a linear transformation from R3 to R2. So now the question is, if I want A, I know the column space is spanned by this, so I can at least say that perhaps the column space of A has these two vectors, 1, 2, 5, 6. Question is, what would be my third vector so that I can achieve what I want? How should I make the null space be equal to, the basis of null space be equal to 1, 1, 1? Well, if you think a little bit, all we are saying is that if you take the first column multiplied by 1, second column multiplied by 1, then choose a third column multiplied by 1 so that you end up getting a 0, 0 vector. So if you look at it this way, life becomes fairly straightforward. So what we are asking is, let me repeat it, that we want, say, something like A times 1, 1, 1 to be 0, 0. This is what we are after. So A times 1, 1 would mean the vector 1, 2 times 1, the vector 5, 6 times 1, and let me call the third vector as alpha beta. times 1 should give me 0, 0. So this tells me that I can choose alpha to be minus 6 and beta to be minus 8. And once I do this, then I have what I want. I have a matrix A whose column space is spanned by these two vectors and whose null space is spanned by the vector 1, 1, 1. So courtesy rank nullity theorem, we can do a lot of things nicely, and we can take it from there. How much time?
How long?
How long have we been recording this?
I don't know. I'm trying to find calculator. We started at 5:50.
5:15.
50.
5:50.
So about an hour.
About an hour. So maybe another 5 minutes and then we. Okay. So now that we have the description of a rank nullity, we can now try to define the remaining two spaces, the row space and the null space, the left null space. Okay. So let's see what is the description for a row space. Generally, to avoid confusion, I would denote the row space of A as this. I don't want to use the letter R because sometimes we use it for reduced echelon form, sometimes we use it for rank. So, as one would expect, definition of row space is very straightforward. It is the space spanned by the rows of A. Just like the column space is the space spanned by columns of A, this is the space spanned by the rows of A. Okay, what does it mean? It means nothing, and it means everything in a manner of speaking. If you think about it, when I say space spanned by rows of A, I would be really interested in the space spanned by the rows of A that have the pivot entries. Or the so-called pivot rows of A. Because anything which does not have a pivot entry must be a dependent row, and hence it really is not contributing anything extra or new. So space spanned by rows of A or space spanned by the rows of A that have the pivot entries should be one in the same space. And in fact, that thing helps us open a new possibility for us. So let me try to show you what I mean by that. Suppose I am given a matrix A, say 1, 2, 3, 2, 4, 6, 3, 6, 9, and just add something more. How about something like this? So suppose this is my matrix A. I can give one description of row space of A, row space spanned by all these three things. But at the same time, I can try to row reduce it and perhaps get to this form. It says 1, 2, 3, 0. This will give me a 0 row, and this will also give me a 0 row. So if you look at this, here is my pivot entry. Namely, this is my pivot entry. So this is my only pivot column. So there is only one pivot, and basically this tells me that the rank of this matrix A is 1. So if I went for the column space, suppose I want the column space, forget about row space for a moment. I would say column space would be just spanned by one vector, which is the pivot column vector. Everything else is actually an R has to come out of this somehow. Let's see. Did I do the correct reduction? I'm just trying to check. No. My bad. I had totally different example in mind when I wrote this. So let me do it again. This is not the row reduced form of it. This will give me 1. And this is 0. Yeah. My fault. I made the wrong computation. So now I will say that I have 2 pivot entries, and they correspond to the first column and the fourth column. So if I want the column space of A, I would aim for the first and the fourth column. So the rank of A is 2. Column space of A is spanned by one, 2, 3, and 0, 1, 1. Okay. What about the row space of A? Row space is spanned by, remember, row space is the space spanned with the rows that have the pivot entries. So I can say rows space is spanned by row 1, 2, 3, 0 and 2, 4, 6, 1. However, if you think a little bit, I can give you one more description of the row space. In fact, I could have used the row reduced version of it and could have said the row space is row space is spanned by those 2 vectors also. Now, at this point of time, one may question my wisdom. When we are dealing with column spaces, we said I can't use the column space of this guy because this column space could be different from this guy. However, in case of row space, I'm saying that the row space generated by the pivot rows here should be the same as the rows generated by pivot rows over there. And why should that be true? If you think a little bit, it boils down to the same technique that I used a little while ago or in the previous lecture, when I claimed that if you can generate the generators, then things will be okay. So for example, any row that I get in the reduced form is actually the linear combination of the rows over here. So the row space of R should be a subset of the row space of A. Likewise, I can reverse all the row operations, and I can start from R and write A. So every row of A is nothing but a linear combination of rows of R. So every row of R is a linear combination of rows of A. Every row of A is a linear combination of rows of R. So their span must be the same. And that is why we have an advantage when we deal with the row space, that I can deal with either these set of vectors, or I can come here and use my row reduced form to get perhaps a simpler set of vectors which will span the space. Okay. There's one point I would like to end with is the following thing. It is this question that we like to answer. What is the relation between the null space of A, the column space of A and the row space of A. So some obvious facts which should be clear by now is that the dimension of the row space of A and the dimension of the column space of A must be the same and must be equal to the rank of A. However, don't expect that the row space and the column space would be the same thing, because it's kind of obvious. Out here the columns live in R3, so whatever they span, things will be living in R3. Rows live in R4, so whatever they span will be living in a totally different space, R4. So of course row and column space need not be the same. So in general, the row space of A is not the same as the column space of A. If it so happens, it's a very, very special case, and you can sort of guess when will that happen. Think in terms of invertible matrices and you may find the answer over there. But still, what is the connection between the null space of A and the column space of A, or the row space of A? So before we answer that question, let me ask you another question. And it has something to do with a little bit of geometry. Can you find me a linear transformation or a matrix A, 2 by 2 is fine, such that its row space is spanned by the vector 1, 1, and its column space is spanned by this, and its null space is spanned by this vector 0, 1. So what I'm saying is, column space of A has 1, 1 as a basis, and the null space of A has 0, 1 as a basis. Can you find such a linear transformation? Obvious approach would be that, okay, fine, I'm going to apply my rank nullity theorem. Rank plus nullity in this case would be 2. So my domain of my linear transformation must be 2. But remember, I already told you can find a 2 by 2 example. So I have already taken care of that condition. Is it still possible for me to find a row space and a column space, a matrix with that column space and that null space? If you think a little bit, you will get the answer to the question that I posed here. What is the relationship between null space and row space? So we'll start with this question next time, and then we'll see the connection between the two things.